We are going to look at two applications of the transportation problem. The first application is the production and inventory control problem. And in this problem, let's assume that a company produces backpacks from March to June, and there's a holding cost. That means if they produce a backpack in a certain month and then sell it in the following month, then they would have to incur a holding cost of 50 cents per unit per month. So if they hold it for 2 months, that means they incur twice of that amount, which is $1, and so on. And there's also a back order cost, which means that they can sell an item and they produce it later. Okay, so they can sell it now but produce it later. For example, if you sell an item or to satisfy the demand in month 1, but you produce it in month 2 or 3, then this is called back order. And there is a $2 cost per unit per month for each month back ordered. So for each item produced next month and sold this month, there's a $2 cost. The cost of production of these backpacks is $40. So how would the transportation table look like in this case? We have here the supply SI, and we have the demand DJ, and we have 4-month supply and 4-month demand. And when there is an arrow from 1 to 1, that means how much to produce in month 1 to satisfy the demand of month 1. And when there's an arrow from month 1 to demand period 2, that means how much to produce in month 1 to satisfy the demand in 2, and so on. So an arrow from supply I to demand J would be how much to produce in month I to satisfy the demand in month J. Here's a transportation table that goes along with the same network, and it shows that the cost of production, which is the transportation cost in this case from March to March, which means that you produce an item or a backpack in March and you sell it in March at a cost of $40. But if you produce something in March and you sell it in April, that means you have left it in inventory for 1 month, which is 50 cents on top of the production cost, the $40. That means the total transportation cost, or the production cost in this case, would be 40.5. Similarly, if you produce something in March and you sell it in May, that means you left it in inventory for 2 months, which is twice the 50 cents, which is $1. On top of the $40 production cost, that will give you $41. And similarly, this 41.5, because this was left in inventory. If a backpack was produced in March and left in inventory for 3 months at the cost of $40 plus the $1.5 of holding or inventory cost. The same thing for the month of April. If you produce something in April and you sell it in April, the cost will be $40. But if you produce something in April but you sold it in March, that means this is what we call a back order, because you produce something after you sold something and then you produce it later. So the back order cost is $2 in addition to the $40 of production cost. That'll give you 42. So that means anything the diagonal will be $40 because you are producing something and selling it in the same month, while the below the diagonal would be the back order, and that would be incurred $2 per month, and above the diagonal will be the inventory cost, and which will be incurring 50 cents per month. And these are the demands, and here's the supplies, obviously. So this is the transportation table for the inventory and production problem. Another example is the equipment maintenance, but I'm gonna skip that in the interest of time. So equipment maintenance will be skipped in this slide and the following slide. This is the transportation table for the equipment maintenance, which is not included, I guess. Okay, so a transportation problem will have feasible solution only when the supply equals to the demand. So if the supply does not equal the demand, we will make the supply equals the demand by either adding a dummy or imaginary, which we refer to it as dummy destination or dummy demand. Uh, for example, in this case, the total supply was 250 and the total demand is 200. So that means that the demand is short of the supply by 50. So I will create a dummy or a dummy demand or destination, which is equal to the difference between the 250 and the 200, which is 50. So I will insert a dummy or a new demand or destination with a capacity or demand of 50, and the costs associated with this dummy destination will be zero, the transportation cost. So all the cells that have that dummy destination would have zero. So, and also, if I want to prohibit a certain connection or transportation route from any I to any j, I would insert a very large number, which is called m, which will prohibit any transportation from that source to that destination. So, integer solutions property unimodularity. And unimodularity, it means that the solution will have to be an integer. And to guarantee that the solution is an integer, sometimes we have to solve the problem as an integer linear program, instead of solving it as a general linear program. And that takes more complexity and to solve this problem. But due to the fact that the supply equals the demand, so the problem is balanced, the supply equals the demand, we call it a balanced problem. The solution will be integer by itself without doing anything extra. So as long as the SIs and the DJs are integers and the problem is balanced, then the solution will have to be integer solution. So now how do we solve a transportation problem? As I said earlier, since a transportation problem is nothing but a linear program, so we can use the simplex method to solve it. However, because of its special structure, being a network, there is a simpler algorithm which is called the transportation simplex method, which is faster to perform the various iterations to get to the optimal solution. We will take a look at this approach. So the transportation simplex method starts by identifying an initial feasible solution, just like with the simplex. So initial corner point feasible solution, and whether this if this this current corner point feasible solution is optimal. If yes, you stop. If it's not optimal, you move to an adjacent corner point, which is better than the current corner point, and you go back and ask yourself whether it's optimal or not, and you iterate. So this is an iterative procedure, just like the simplex method. But how does it work in details? We're going to see that in the next few slides. This is the anatomy of the transportation simplex tableau or the transportation tableau. As I told you, these are the sources. There are m sources, n destinations, and in the sources you have the various supplies, and in the destinations there's n of these destinations, and you have the various demands. And as I told you, and of course the cost of Cij of transportation. And as I told you, there is the problem must be balanced. So that means if I sum up all these SIs and all these DJs, they should be equal. And if they're not equal, I'm going to have to create either a dummy source or dummy supply with a capacity equal to the difference, and I will insert into this table. I will see that in the next few slides too. So here we see an example, transportation problem with three sources and three supply sources and four demand centers, and the capacity of each supply is 200, 350, and 150, and they add up to 700, while the capacity or the requirements on the demand center is 100, 140, 300, and 250, which they add up to 790, which means there's a difference of 70. That means I have to create a dummy supply with a capacity of 90, which is the difference. And we're going to see that in the next slide. Here we see the dummy, which was inserted as a dummy source with a capacity of 90, which is the difference between the 700 and 790. And note that we have the costs, transportation costs from or to the dummy of zeros. Always the transportation cost from a dummy or to a dummy will be always zero. And this is the transportation table. I would want to solve it now. And as I saw in the previous slides, that the first thing that I need to do is I need to have an initial feasible solution, and that's what I will do in the next few slides. And there are many ways, but there are three popular ways of finding an initial feasible solution, and these are the northwest corner rule, the first one here, and then the least cost rule and the Vogel's rule or method. The easiest one is the northwest corner rule. We're going to look at three of them, but let's start with the first one, the northwest corner rule, as follows. Here's the algorithm. How does the northwest corner rule work? But I will simply show you in the next slide how does it work really. So basically, the method says allocate as much as possible to the northwest corner. In this case, it's the upper left corner. This corner is the northwest corner, always the upper left. Allocate as much as possible. That means here's the demand for this N node is 100, and the supply for this A node is 200. And this was the 100. So that means if you want to allocate as much as possible to this node shipping from node A to node N, you cannot ship more than 100 because that's what the capacity of the demand for this node is. Although there's a larger capacity here of production, but you don't want to ship that. So it's the minimum of those two numbers would be 100. So allocate as much as possible to that node, which is 100. Once you allocate that, so basically we tick that off and we update the number here, and now it's 100 instead of 200, and now we temporarily also remove that column, and then the method says repeat. That means where is the new northwest corner now? Now the new northwest corner is here, and it says allocate as much as possible, and in this case 140 here and 100 here. The maximum or the minimum, sorry, is 100. That means you allocate 100, and in this case this becomes 0 and this becomes 40, and we remove the one that is 0 temporarily like we did in the first one, but this time it's the row, not the column. It's removed temporarily. So where is your next northwest corner? Would be this one, and this is allocate as much as possible. What's the minimum between 40 and then 350? It's 40, so this 40 becomes 0, and then this 350 becomes 310, and I remove the column temporarily like this, strike it out, and then there's a new northwest corner which is here. Allocate as much as possible between 300 and 310. This is the minimum, so this becomes 0 and this becomes 10, and I remove this column temporarily, and this is the new northwest corner now. Allocate as much as possible 10, so this becomes 0. This will go away, and then the new northwest corner will be this one. So the minimum is 50 and 250. I will put 150, so this becomes 0, and this becomes 90. So, and this will go away, and then there's the north is the only cell, which is the northwest cell now, and I allocate 90 to it because it's equal now, and that's how it should end up like this. By the way, you should have the same number in all three, in this here and there, and then 90 here. So this is it. So this means this is the where I allocate this is an initial feasible solution where I allocated a ship 100 units from A to N, ship 100 units from A to S, ship 40 units from B to S, ship 300 units from B to E, ship 10 units from B to W, and ship 150 units from C to W. Obviously, the dummy doesn't mean anything here because the cost of that is 0 anyway, 90 times 0. So what's the cost of this assignment or transportation assignment? The cost is I'm shipping 100 at a cost of 16 per unit, so 100 times 16 plus 100 times 13 plus 40 times 13 plus 300 times 19 plus 10 times 15 plus 150 times 10 plus 90 times 0, a total of z equal 10, 770. This is the total cost. Now the question is this optimal or can I do better? Can I have a cheaper transportation cost to satisfy the various demands and not to violate the various capacities of the production sources? So in the previous slide, we've seen the rule, which is the northwest corner rule, which allows you to start or to find an initial basic feasible solution. Before we proceed with, okay, how do we get to the optimal solution? This is another way of having or finding an initial feasible solution. It's called the least cost rule. And again, this is the algorithm. You can take a look at it, but in the next slide, I'll show you how does the algorithm work. Instead of starting with the northwest corner like we did in the northwest corner rule, we start with the least cost. That means I look at all the table here, all the table, and I find the least cost, the minimum number in the cost, transportation cost. The zero is the minimum number, obviously, so I will take any one of these zeros. So ties are broken arbitrarily. So here's the minimum cost is 0. I take this one instead of that one or that one, it doesn't matter. I start here, so allocate as much as possible to this cell. Means that here's 100 and here's a 90. The minimum is 90, just similar to the northwest corner rule. That means the minimum is 90, so allocate 90, and then this becomes 10, and this becomes 0, and we will have to remove temporarily the row or column that has a 0 next to it. So this is 1. So now from whatever left in the table, I will look at the least costs here. And look 9, 14, 16, all over the table. I find out that 9 is the least cost, so allocate as much as possible. Since there's a 10 here, and there's a 150 here, the minimum cost is 10, so allocate the 10, and this 10 becomes 0, and it will go away, and this 150 becomes 140. Now, from whatever left from the table, which are these, um, find the minimum cell. In this case, it is the cost of 10, I think here, right? And 10 is the minimum cost, so allocate as much as possible. 140 and 250, the minimum is 140, so allocate 140. This becomes 0, and this becomes 110, and the 0 goes away temporarily, and I'm left with the first 2 rows only, and I will find the minimum from those costs. The minimum turns out to be what, 13 here. That's right. There are 2 minimums, but pick whichever one arbitrarily. There are 2 to the 13s, so I take this I picked this 140, so I picked this 13, and means that allocate as much as possible. So 140, this becomes 0, and this becomes what I think 210. So I will remove this column. I'm left with those cells here only, and I will pick the minimum, and I repeat until I'm all done. So is this optimal? How are the cost first? Yeah, the cost, I'll get it by multiplying 200 by 22 plus 140 by 13 plus 100 by 19 and so on until I get the new cost. So this cost may or may not be smaller than the other cost in the one that I calculated using the northwest corner rule, but most likely it is better. That means it's smaller. Anyway, okay, the third method to find an initial feasible solution for the transportation problem is the Vogel's method, and it's the one that uses more calculations than the others actually. And they say it usually provides you with the closest answer to the optimal solution, if not the optimal solution, but there's no proof to that anyway. So the method works as follows. You take for each row and column, take the minimum, the smallest two costs, Cij, and subtract them from each other. And then uh, select the row and column with the largest number of this difference. And then for that row or column that has the largest difference, select the minimum cost and then allocate as much as possible to that cell, and then update the supplies and demands, and then repeat. So let's look at how does it work. So here's the difference, minimum, the smallest twoCijs for this row is what? Is the 13 and the 17. The difference is 17 minus 13 is 3. So this is the first difference. Then for the second row, we have the smallest two are 13 and 14. The difference is 1. And so on. The smallest two in the third row would be 9 and 10. The difference is 1. And the smallest two in the fourth row is 0 and 0, so 0 minus 0 will be 0. So we'll repeat the same thing for the columns. The columns we have, obviously the smallest is 0 and the second smallest is 9, so 9 minus 0 is 9. In the second column we have, obviously we have 0 all the time as the smallest, so the second smallest is 13, either one of these. So will be 13 minus 0 is 13, and then with the smallest would be 19 minus 0 is 19, and then we have 10 minus 0 is 10 for this fourth column. So the largest penalty, and you break ties arbitrarily if you have more than one, but here we have only 119, which is the largest penalty. So we'll take then this column with the largest penalty and select the smallest cost within this column, which is here. So we're going to see that in the next slide. So allocate as much as possible to this cell. In this case, we have 300 and we have the 90. So we update the 90. It becomes 0 and the 300 becomes 210. And then you remove this whole row and then you recalculate the differences. Okay, so once we recalculate the differences, you'll see that in the next slide. So the new differences are, these remain the same because we just removed the fourth row. So 3, 1, and 0, 3, 1, and 1 remain the same as row differences. How about the column differences? Because we removed this dummy row, they will change. So it's the smallest two costs in the first column are 9 and 14. So 14 minus 9 is 5. And then we have 13 and 13 is 0, and then you have the difference between the smallest two costs in the third column to be 3, and the smallest two costs in the fourth column to be 5, being the 10 and the 15. So again, what we do here, we select the largest difference. In this case, it is 5, and then with it's either the first column or the fourth column. We select either one of them arbitrarily, and then we allocate, and then we find the minimum cost cell in that column, and then allocate as much as possible to it. In this case, I have selected the first column to be the one with the largest difference, and then 9 being the smallest cost in that column. And then I'm going to allocate as much as possible to this column. So we have the 100 here, and we have 150 on the supply. So that means the minimum of the 100 and 150 is this 100. Allocate as much as possible to it, which makes this 0, and this will go away. And this becomes 50, obviously. But then again, once I remove this first column, I'm going to have to update the differences and recalculate these differences and repeat the same procedure until I have assigned all these numbers. Here, the updated differences are, after removing the first column, are 4, 2, and 10. Obviously, these are calculated from for example, this 4 here is calculated from 13 or 17 minus 13, the smallest two costs, which is 4, and similarly this 2 is calculated from 13 minus 15, and so on. I recalculate also these differences for the columns, so 0, 3, and 5, which are the differences for the columns. I select the largest difference, which is now, in this case, it's this 10, and within the third row, the smallest cost is 10. So this is the cell that I want to allocate as much as possible to it, and obviously because of this 50 and this 250, the minimum is 50. I'm going to allocate 50 to this cell, as we'll see in the next slide. I update the differences. I remove the satisfied column. This means this will go away. The third row will go away, and then I will update again the differences, and I will go with the largest difference. This time the largest difference is 4, and then the smallest cell in this first row would be the smallest cost would be this 13. Allocate as much as possible to it, so it's the minimum between 140 and then the 200, and it's 140, so allocate 140, and then obviously this becomes 0, and this becomes 60, and then I need to update the differences also, but also this will allow me to get rid of this column, and so on. So the next one would be the largest difference is also this 5. Allocate as much as possible to the smallest cost in this row, which is here 60. Why? Because it's the difference between this 60, which becomes 0, and this 200 that becomes 140. But it allows me to get rid of this row now. And then what's left here is those. We can take the smallest is 15, allocate as much as possible to it, and the algorithm is done. The cost of that allocation or transportation plan is 10,330, which should be smaller than the first two calculated ones. Now, we can use any one of those three methods to find the initial solution to the transportation problem. But once we have initial solution, we have to subject it to this optimality test. That means, is the current solution optimal? If it's optimal, then I stop, I'm done. But if it's not optimal, I'm going to have to find another solution, which is another corner point solution that will improve the current solution. And the way we do this is by first finding what we call the dual variables of the transportation problem, and we're going to see that in the next slide. But just remember that this formula that we're going to use in the next slide, that for all basic variables, we're going to use this formula ui plus vj equals cij. While for all non-basic variables or cells, we're going to use this c prime ij equal ui plus vj minus cj. Okay, now once we have an initial basic feasible solution, and this was the one obtained by the Vogel's method, we will need to check whether this is an optimal solution or we can improve the solution further. To do so, we need to calculate what we call the dual variables or the multipliers ui and the vj. And the way we calculate these, from the previous slide, it says ui plus vj equals cij for all basic cells. So I take a basic cell. Here's a basic cell. All these cells that have circles inside them. This is one of them. It's the basic cell. So that means it's a basic variable. The cells that have nothing inside them, like this one, is not a basic cell, and because it's empty. So for every basic cell, ci plus vj, ui plus vj equals cij. So I start with ui equal to 0 all the time. Ui equal to 0. Now ui for this basic cell, ui plus vj, which is something, equal to 13. What is this something? So that means 0 plus 13 is equal to this 13. ui, this one, which I by assumption started to be 0, plus something equal to 13. This something is 13. So I continue doing so until I find all the ui's and the vj's, which are the dual variables or the multipliers they are called sometimes. I'll take this other basic cell, ui 0 plus something here equal 17. This something must be 17. Now I can do this one now. This is U1, this is U2. This is U1, this is U2, U2. How can I find it? I'll say 17, which I just found right now, plus something, the U2, equal 15. This something must be what? Minus 2. So minus 2 plus 17 equal 15, and so on. Similarly, U3 can be found the same way. We'll say that 17 plus U3 is 10. What must this U3 be? It will be minus 7. I can continue like this. I'll see this already made calculated for us in the next slide anyway. We continue in this manner until we find all these ui's and the vj's in here by simply looking at all the basic variables. Now once I have all the ui's and the vj's, I'm ready to calculate the c prime ij, which is a number I calculate for the non-basic variables, all these empty cells. So for all these non-basic variables, the value of c prime ij equal ui plus vj minus cij. So for the first c prime ij here, 0 is calculated from ui 0 plus vj 16 minus cij 16 is 0. This one, minus 1, is calculated from 0 plus 21 minus 22 is minus 1. This 0 similarly is calculated from -2 plus 16 minus 14, which is 0. So, and so on. Once I have all these C prime ij's, which I'm going to circle now, I will look at their values. The problem is optimal if all the C prime ij's are negative, or zeros or negative. And the problem is not optimal if there exists at least one C prime ij which is positive. And in this case, all the C prime ij's are negative or zeros, which makes this problem optimal. Now, if the problem is not optimal, that means I have one of those C prime ij's to be positive. If I have more than one, then I will select the most positive. If I have only one, I will select that one. And this will be my entering variable, which we'll deal with it in our next lecture. Here's the final optimal solution then. As I told you, using the Vogel's method will put us very close or at the optimal solution, and it is how we found the optimal solution for this problem without further iterations. But in case this wasn't optimal, then as I told you, we need to find the entering variable, and the entering variable would be the cell that has a C prime ij positive, or the most positive C prime ij. Okay, we will continue next lecture.